this is the algorithm most people start with when studying machine learning, and it's called the linear regression algorithm. So let's have a look at what the linear regression algorithm is all about. So the problem statement of linear regression is that we have a labeled data set containing tuples of features and labels. So we are in a supervised learning scenario since we have labels available. Also, this time we assume our features X to be of a particular shape. So we assume them to be d-dimensional real-valued vectors. And they have the following form. So xn, the nth feature vector, is a column vector. So on this slide, I denoted it as a row vector transpose, just to save some space, but actually it is a column vector. The first entry, the first feature, we call xn1, second feature we call xn2, and so on, until we reach the end of our nth feature vector, which is the dth feature, and we call that one xnd. And since we are in a regression scenario, we have that our output labels yn are just real numbers. Now the linear regression algorithm assumes a linear relationship between the inputs and outputs. And this linear relationship looks like this. So we have the nth label yn, and this will be a linear combination of our features, as well as some bias term and some noise. So the bias term describes our expectation of the label in absence of any observation of the feature vector. And the noise term is just the difference between the true label and our model. This is our model. And what does linear regression look like actually? So let me draw some data points. Now imagine we are in this 2D case. Well, actually, the feature vector is only a scalar in this situation, so it contains only of one feature. Then the linear regression model that we will find will be the line of best fit to that data. And in a future slide, I will make very explicit what I mean with the line of best fit. But I hope you see that such a line would describe the relationship between the x's and the y's quite well. So of course there's deviation. These are the epsilons. But still, this is a pretty good fit to our data, wouldn't you say? So in this particular linear regression scenario, we have to find two values. First, the intercept, the bias, WO, which is where the line, our model, intersects with the y-axis. And the slope of that line with respect to the feature we have available. And this will be W1. We could also be in a 3D case where we have two input features, x1 and x2, and we want to predict the label y. So this time data points live in a 3D Euclidean space, and our linear model would be a 2D hyperplane. This is a 2D hyperplane. Instead of a single line, we will have a 2D hyperplane, a linear one. And this time we have to learn three parameters. So WO, the intercept, and then the two weights corresponding to our two input features. So W1 for x1 and W2 for x2. Of course, given this problem statement, nothing stops you from doing linear regression in d-dimensional space, where d might be much, much larger than what I'm able to draw on this slide. You'd just have to find d plus 1 parameters. What we'll now do is called vectorizing our hypothesis for a single observation. So what does it mean? On the previous slide, we have seen that our model, our hypothesis, is a linear combination of our features plus some bias. And what we would like to have ideally is that we can produce a prediction y hat n using a vectorized implementation. The vectorized implementation is an inner product of two vectors. So what we'll need is a new parameter vector w, which is a column vector containing all the parameters or coefficients of our linear regression model. So it will contain WO, W1 until WD, and it will be a D+1 dimensional real valued vector. These two vectors are not of the same dimensionality, right? So even though we want this implementation, we cannot do it just yet because xn is of dimensionality d, whereas w is of dimensionality d+1. So we cannot actually compute the inner product of two vectors that have different lengths or dimensionalities. But we can easily fix this by just adding a 1 as the first component of our feature vector xn. And it will look like this now. So the first entry will be a 1 and all the other entries will then follow. And now, since both vectors have the same dimensionality, we can calculate their inner product. And just as a side note, we want this vectorized implementation because calculating inner products is much more efficient in your computer than calculating sums iteratively. And now we want to vectorize our hypothesis, our model, for the entire dataset, not just for one observation. And recall, in our dataset we have n of such observations, and what we just do is that we define this matrix X, capital X, where we stack the transposed individual feature vectors x1 to xn. And writing this out explicitly leaves you with this definition of our feature matrix. Now the first column is just the one that we add in order to be able to include the bias or the intercept in our model formulation. And the rest of each row corresponds to the original observations that we have, the original feature vectors. This is the original x1, this is the original x2, and this is the original xn. And this feature matrix has the dimensionality n times d+1. I hope that you can see this. This is n many rows and d+1 many columns. Recall that for one individual observation, we have that the inner product between the corresponding feature vector and the weight vector will be your prediction for that particular observation. So let me write it out again. The nth prediction is the inner product between the nth feature vector and our weight vector. And now we want to stack all of these predictions into one column vector. Again, this is a row vector transposed so that I can actually put it on a slide, but this is a column vector containing all our n, capital N, predictions. And we arrive at y hat by multiplying our feature matrix X with the weight vector W. And to see this, let's consider the dimensionality of X and the dimensionality of W. And by looking at these dimensionalities, we see that the multiplication of X and W is defined because the second dimension of X and the first dimension of W correspond. So we can actually multiply them. And the resulting object is of dimensionality n times 1. N times 1. Which is just Rn, and this will be our prediction vector. If you're still not convinced that this will produce our vector of predictions, then you could, of course, calculate this by hand using this definition and the definition of the weight vector, but let's just proceed. And similarly to the predictions, which we all stacked into a column vector, we can do the same for the true labels that we have available. And of course, this object will then also be of dimensionality n because we have capital N many true labels available. And now recall that for our model formulation, we have for each observation this epsilon term, which is the difference between our model prediction and a true label. And now we want to stack all these epsilons into a vector, which we will call epsilon underscore. And of course, this will also need to be of dimensionality n. How do we arrive at this object? So again, epsilon is defined as the deviation between our prediction and the true label. And if we do this for each observation we have available, you will see that this is just the prediction vector minus the true label vector. And this will be our error vector epsilon underscore. So in the last lecture, I introduced the empirical risk minimization procedure. And we want to do the same now for this linear regression problem. So what we need is a loss, right? Because the risk is only defined with respect to some loss. And this loss we want to define on the entries of our error vector epsilon. And what we'll utilize is what's called a vector norm. And a vector norm is a function that takes as input a vector and produces some measure of magnitude for that vector. But let's define it formally. We call this mapping, which maps from Rn to the positive real numbers, a vector norm, if and only if the following properties hold. So this first property is called definiteness, and this means that for every vector v in our input space, we want to have that if our mapping assigns a 0 to that particular vector v, then this should imply that v is the 0 vector in Rn. So there should be no exceptions. The only vector that is capable of producing a magnitude, think of a norm, a vector norm of the magnitude of a vector. The only vector that should produce a magnitude of 0 should be the 0 vector. The second property is called the absolute homogeneity. And for this, we want that for every vector in our vector space and for every scalar over which the vector space is defined, we want the following equality to hold. So the magnitude of the scaled vector should be equal to the absolute value of the scalar times the magnitude of the unscaled vector. So what this means is that we want our vector norm to acknowledge the scaling of a vector. So for example, if I have a vector that has magnitude 1 and I scale it by the factor of 2, then this should produce a 2 as well as this side. And it does so by saying, okay, the factor is 2 and the magnitude of the untransformed vector, the unscaled vector, is 1. So we have 2 times 1, which is also equal to 2. And now there's the absolute value of the scalar. And we have this because if I were to scale my vector by a negative factor, -2 for example, then it would still be twice as large, but it would point in the opposite direction. But the direction doesn't matter for calculating the length or the magnitude of that vector. So we just take the absolute value of the scalar. And the final property of vector norms is called the triangle inequality. And for this, we want that for every vector pair uv in our vector space, the following is true. So the magnitude of the sum of the two vectors should be smaller or equal than the sum of the individual magnitudes. And this is a small illustration that hopefully gives you some intuition of why this is a useful property to ask for. Now imagine these are paths that you could take and you start at this point and you want to arrive at this one. Now the two options that you now have is that you go first into the u direction and then into the v direction, and then you arrive at your point of destination. But what is always at least as quick or quicker than going into the u direction first and then going into the v direction is to go into the direction which is defined by the sum of these two. And this triangle inequality tells you that adding this magnitude with this magnitude should always be at least as large as just finding this magnitude. Now what I want to do is to give you a proof of a direct consequence of these vector norm properties, and that is norms are convex in the vector elements. Now I understand that not everyone watching right now knows what convexity means. So if that's the case for you, then don't worry. I'm going to explain convexity in depth in a few slides. So consider this slide optional if you don't know about convexity and refer back to it once you've seen my explanation of convexity. But I just want to do the proof now because, again, it is a direct consequence of the vector norm properties. So if you know about convexity, then this one is for you. So what we want to show is that norms are convex in the vector elements. And for this, we need the following. So this is the definition of convexity for a function. And we have that our vector norm is convex if and only if for every vector combination uv in our vector space Rn and every scalar within the unit interval, we have the following. The magnitude of this vector, lambda times u plus 1 minus lambda times v, should always be smaller or equal than lambda times the magnitude of u plus 1 minus lambda times the magnitude of v. And in a moment we will see that we can easily arrive at this conclusion using the vector norm properties. So let's get started. So for vector norms, we always have that for each vector combination uv in our vector space Rn and every scalar lambda within the unit interval, we have the following. So the magnitude of that vector, so we start with this left-hand side, the magnitude of that is always smaller or equal than the individual magnitudes of these two scaled vectors. So the magnitude of lambda u plus the magnitude of 1 minus lambda v. And this is a direct consequence of N3, the triangle inequality. But we're not finished yet, right? Because this quantity isn't this one yet. So as a consequence of the absolute homogeneity, we can push out these scalars, the absolute value of these scalars. So observe that we're almost there. We just have to realize that since lambda lives in the unit interval, the absolute value of lambda and 1 minus lambda will be just lambda and 1 minus lambda. And with that, we have shown that norms are convex in the vector elements. So now we have formally introduced norms, vector norms, which is a way to measure the magnitude of vectors. But now we'll also introduce metrics, which is a way to measure the distance between 2 points. So we have the following definition. We call the mapping D, which takes as input a tuple of n-dimensional real-valued vectors and produces a positive real number. A metric, we call this mapping a metric, if and only if the following properties hold. So first is the null distance, which means that for every vector in our vector space we have that the distance from v to itself will be 0. So this makes sense for a metric, a way to measure distance, right? Because the distance from one point to itself should be 0. Next is the triangle inequality again, and for this we want for every possible vector triplet u, v, w in our vector space Rn that the distance from u to v plus the distance from v to w should always be larger or equal than the distance from u straight to w. So we can employ the same intuition again as we used in understanding the triangle inequality for vector norms. And that is going from u to v and then from v to w should always be as long or longer of a way than going from u straight to w. And then there's the symmetry property, which means that for every vector combination uv in our vector space Rn, we want that the distance from u to v is equal to the distance from v to u. And this also makes sense, right? Because we don't want the order of our arguments for a distance function to matter. The distance from one point to another is the same as going back the same way. And then finally there's positivity. And this means that for every vector combination uv in our vector space Rn, we have that if these two vectors are not the same, so they correspond to different points in space, then we have that the distance between them is not equal to 0, and instead it's some positive distance. And again, this also makes sense intuitively, because if you have two different points, there will be a distance between them. Now you'd be justified to ask yourself, okay, why do we introduce these abstract notions of measuring magnitudes of vectors, as well as distances between points? So of course there's a reason why we introduce these notions, and for you to see this, let's introduce this norm, any norm. Using that norm, we can easily find a distance metric between 2 points, or 2 vectors u and v, as follows. It's the magnitude of the difference between these 2 vectors. And we call this distance metric the metric induced by our norm. And now recall that our error vector epsilon underscore is defined as the difference between our prediction vector y hat and the true label vector y. And now if we measure the magnitude, the norm of our error vector epsilon underscore, we have that this is equal to the magnitude of the difference between the prediction vector and the true label vector. And since this expression corresponds to our metric induced by some norm, we have that this corresponds to some metric that takes as input the prediction vector and the true label vector. So what we effectively do by measuring the magnitude of epsilon underscore using a norm is that we measure the distance between our prediction vector y hat and the true labels. This is the distance between the predictions and the true labels. So on the previous slide I just gave you the statement that if you take the magnitude, the norm of the difference of two vectors, that this qualifies for a metric. But let's do it formally, let's prove this. And what we would like to show in this context is that if we define a metric as the magnitude of the difference between the two arguments, that this satisfies the metric axioms M1 to M4. So let's do them one by one. Let's start with M1. So recall that M1 was the zero distance property. So if we have a vector v in our vector space Rn, and we take the distance from v to itself, then this should be equal to 0. And this holds true for the metric induced by some norm, because if we translate the metric into its norm formulation, we see that the distance from v to itself is equal to the magnitude of v minus v, which is equal to the magnitude of the zero vector. And the first norm property we have is that the zero vector produces zero magnitude. So we have that the metric induced by some norm satisfies M1. So M2 was the triangle inequality for metrics. So we want the distance from point u to v plus the distance from point v to w to be larger or equal than the distance from point u straight to w. And this is true for a metric induced by a norm, because if we translate this metric into its norm formulation, then we see that the distance between u and w is equal to the magnitude of u minus w. And we can simply add and subtract the vector v inside this magnitude. And from the triangle inequality for norms, we have that this expression, the magnitude of that vector, is smaller or equal than the sum of the individual magnitudes of the vectors u minus v and v minus w. And if we translate them back into what they look like as metrics, we have that this one corresponds to the distance from u to v, and this one corresponds to the distance from v to w. And with that, we have shown that M2 holds for metrics induced by vector norms. Now we want that M3 also holds, and this is the symmetry of metrics. So the order of the input arguments shouldn't matter. And to see that this holds, we translate the distance from u to v to its norm representation, and this is then the magnitude of u minus v. And we can rewrite u minus v as follows: minus 1 times v minus u. This is the same. And from absolute homogeneity and 2 for norms follows that this is equal to the absolute value of minus 1 times the magnitude of this bit, v minus u. And we observe that the absolute of minus 1 is just 1, so we multiply 1 with the magnitude of v minus u, and this is just the magnitude of v minus u. And then we can translate back into the metric notation, and we see that this is the distance from v to u. So this is a metric. And finally, we want to show positivity. This means that if we have two vectors u and v and they are not equal, then the distance between them should be positive, strictly positive. And you can see that this is a direct consequence of N1, the first property of vector norms. And that is, if u and v are not equal, then this implies that the difference, u minus v, is not the zero vector in our vector space. And this implies that the magnitude of the difference between u and v, which is not the zero vector, cannot be 0. And since the norm maps into the positive real numbers and the 0, excluding the 0 leaves you only with the strictly positive numbers. So this will be positive. And we have now shown that metrics which are induced by norms are indeed metrics. I now want to show you the p-norms, which is a class of vector norms, a family of vector norms, which is defined for real numbers p equal to 1 or larger than 1. So for this, let v be a real valued vector with capital N components. Again, this is a column vector. And then we define the p-norm of v as follows. So this is the p-norm of v. And this is equal to the sum of the absolute values of the components of v to the power of p, the sum of all these terms, these capital N terms. And then finally taking the p root of that sum. And again, the p-norms are defined for this range, so p larger or equal than 1. So I will now show that the p-norms are indeed norms. Let's start with n1. So for n1, we want to show that if the p-norm of v is equal to 0, then this should imply that v is the 0 vector. And we see that this implication is true, because if we write out this expression according to its definition, we see that we have the sum of absolute values of the components to the power of p, and then we take the p root of that sum. And since we are considering only the cases where this entire expression is equal to 0, we have to find out for which cases this is indeed true. And we see that we sum up absolute values of the components, and the absolute values of real components are always larger or equal than 0. And since this entire expression should equal 0, this means that each component needs to be 0 in order to satisfy this equality. So Vn should be equal to 0 for all n, for all components in a vector. And if that's true, then V must be the 0 vector. So we have now shown that n1, the definiteness, holds for the p-norms. Now we want to show n2, the absolute homogeneity of the p-norms. And for this we show that the magnitude with respect to the p-norms of the scaled vector lambda times v is equal to the absolute value of lambda times the magnitude of v. And we can easily show this by just writing out the definition of the p-norms. So we have the p root of the sum of absolute values to the power of p of lambda times the components of v. And we observe that we can push out this absolute value of lambda to the power of p term and multiply it with the absolute value of vn to the power of p. And further we see that since lambda doesn't depend on n, we can push it outside the summation, and then the p cancels with the p root, and we have this absolute lambda term in front of this sum. And this is just equal to the absolute value of lambda times the magnitude of v in the p-norms. Now I would like to prove the triangle inequality for the p-norms, but honestly this is a little more involved than showing n1 and n2. So what we need is Minkowski's inequality, which is a consequence of Hölder's inequality. So we could do that, but it would be just a little too much for what I'm trying to show in this linear regression lesson. So we will actually skip it. I hope that's fine. But if you're terribly interested in the proof, you can look it up. There are demonstrations of this proof on the internet. Now, having talked about p-norms in general, let's look at specific examples for p equaling some value. So the first norm I want to study with you is the L1 norm. And for this, let v again be a vector containing n real valued components. It's a column vector. And we set p to be equal to 1. And inserting p equal to 1 into the p-norms as defined on a previous slide, we have this expression. So the L1 norm of v is equal to the sum of absolute values of the components of V. And here is an illustration for the 2D case. So the vector that we are looking at has two components, x and y. And given the values of x and y, we see that the L1 norm of this vector with the components x and y forms this diamond-like shape. And recall, right after the definition of vector norms, I showed that vector norms are convex, and you can see this. This is a convex function because each local minimum, and there's only one, is also a global minimum. And this is where the components of this vector xy are equal to 0. So the minimum for the L1 norm is the 0 vector. For additional intuition, let me draw a figure. So recall that for any norm, so this L1 norm, for example, we can construct a metric which is induced by that particular norm. And we call this metric D1. And this is equal to the L1 norm of the difference between 2 points. So I've drawn this illustration. Let's have a look. We have 2 points A, which has components x1 and y1, and point B, which has components x2 and y2. And if we calculate the L1 norm of the difference between these 2 points, so the distance between A and B, then we have that we add the absolute value of the difference between the x1 and x2 components and the absolute value of the y1 and y2 components. So measuring the distance from point A to B using the L1 norm amounts to adding the difference between the x components and the difference between the y components. So we don't go straight from A to B, but instead we first go in the x direction and then in the y direction. And this is why sometimes we call the L1 norm the Manhattan norm, because we can only move in orthogonal lines. Similarly to the way the streets are arranged in Manhattan, they are arranged in a orthogonal fashion. Another really common case is for b to be equal to 2, and this leads to the so-called L2 norm. And this is the square root of the sum of squared vector entries, right? So the L2 norm of a vector v is defined as the sum of squared entries and then taking the square root of that. And again, I've prepared a 3D plot for you, this time for the L2 norm. And the vector we measure the magnitude of has 2 components again, x and y. And we see that this also has like a convex shape. So there's the minimum, and every local minimum, and there's only one, is also the global minimum. But this has more of a cone shape as compared to the L1 norm, which is more diamond shaped. And at the edges, we can see that this is indeed a quadratic. And again, since the L2 norm is a norm, we can define a metric which is induced by that norm. We call this metric D2. And this is equal to the L2 norm of the difference between 2 vectors A and B. And if we evaluate this, this is equal to the squared differences of components. We sum these up, and then we take the square root of that sum. And for the 2D case I've drawn above, this will be equal to x1 minus x2 squared plus y1 minus y2 squared, and then taking the square root of that. This might look familiar to you actually, because this is the standard Euclidean distance between 2 points. So this is the shortest path in Euclidean space from A to B. Well, let's study some edge cases for the p-norms. And what I'll do in the following is I'll show that if p approaches infinity, then the p-norm of V will be equal to the maximum absolute entry in V. So to start this proof off, let's define 2 objects. V, which is a n component, capital N component real vector, and this limiting object, the infinity norm of V, and this is equal to the maximal absolute entry of V. I will show that the limit as p approaches infinity of the p-norm will approach this limiting object, right? So let's start. So let's write out the p-norm of V, And this is equal to this definition that we've seen a few times now. And what we can do is we can multiply the limiting object, the infinity norm of V, with that expression if we scale the individual entries we are summing up appropriately, right? So this is equal to this bit. And we now observe that this quantity here is always smaller or equal than 1 because we divide by the largest absolute entry in our vector. And we have that this is equal to 1 if we divide the infinity norm of V with the infinity norm of V. And this happens at least once because there is a maximum element in the vector. And it can happen at most n times. If all the components of V are equal, then all of them are the maximum element. Now this observation leaves us with this inequality. So the infinity norm of V is smaller or equal than the p norm of V. And the p norm of V is smaller or equal than the infinity norm of V times the p-th root of n. Now we observe that n is a natural number. It's always positive. And if we take the limit as p approaches infinity of the p-th root of n, we have that this is equal to 1. And this in turn means that if we take the limit of the p norm as p approaches infinity, that this will approach this limiting object, the infinity norm of V, which is the maximum value of absolute entries in our vector V. Concluding our proof. Now let's look at another edge case. So recall that the p norms are only defined for p's which are larger or equal than 1. And we can ask ourselves, what happens if we set p equal to 0? And the answer is setting p equal to 0 leads to an undefined expression because we have this division by 0, which is not defined. So what we do instead is we define this L0 norm, this bit here, explicitly to be the number of non-zero components of a vector. So for this expression we use indicator variables, and this indicator variable is 1 whenever Vn is not equal to 0, and it is 0 whenever Vn is equal to 0. So if we write out this indicator variable explicitly, we have the sum of branch cases where we add a 1 to our summation if the component is non-zero and 0 if the component is 0. Note that this definition of the L0 norm is generally accepted, but technically it is not a norm. And this is because the L0 norm only satisfies absolute homogeneity for the scalars 0 and 1, not for any other scalar. So this is why the L0 norm is not a proper norm, as we defined on a previous slide. At this point, I want to give you an intuition behind the p norms. So let's first define another object, a closed unit ball. So there are also open unit balls, but we consider closed unit balls. A closed unit ball is the set of points of distance smaller or equal than 1 from a fixed central point. So formally, this means that we have the closed unit ball BP, where p is our value for the p norm. And this is defined as the set of points in Rn for which the p norm of that point V is smaller or equal than 1. And since we know a norm induces a metric, we can find an alternative but equivalent formulation, which is that we have the set of all points in Rn for which the distance induced by the p norm from the origin to that point, the origin is the 0 vector, is smaller or equal than 1. And let's have a look at this illustration to see this in action. So we first considered the case where p is equal to 1, and this corresponds to this shape. So all points within that square, as well as the edges, the points at the edges, these form the closed unit ball with respect to the L1 norm. We recognize this shape, this diamond shape, from the plot that I showed you earlier on another slide regarding the L1 norm. Now the second case that we studied was the case where p is equal to 2. And in that case, the unit ball, the closed unit ball, is actually a circle. And hopefully you also recognize this as the cone shape of the plotted L2 norm on a previous slide. And from this illustration we see that the unit balls, all of these, are convex sets for p larger or equal than 1. So I know I didn't give you a proper treatment of convexity yet. I will do so just in a moment, I promise. So a convex set is any set for which you cannot find a line that connects 2 points within that set and also leaves that set. So for this set you cannot find such lines that leave the set, but consider this set as a counterexample. So you have these 2 points, this one, and the line connecting these 2 points has some section of it outside the set. And thus, this set is not convex. Now looking at this illustration again, we see that all these unit balls are convex because you cannot find a line that goes outside the unit ball. But if we were to consider a p that is smaller than 1, then we would have a unit ball that has this star shape. And we see that such unit balls would not be convex because you could find lines that leave the set. And this should serve as a somewhat intuitive geometrical proof that shows that the p-norms are indeed only norms, proper norms for p larger or equal than 1. Because recall, norms are convex and the set that they induce are also convex. And for p that are smaller than 1, we no longer have convex sets. Now we've talked so much about these geometrical notions of norms and metrics. So let's return to our linear regression problem. And we want to do empirical risk minimization. And for that we need a loss function. And let's define it finally. So our loss function is called E, and it's a function of our parameter vector because this determines the fit to our data. And we will define it as the sum of squared deviations between our predictions y hat and the true labels y over n. We divide it by the number of observations. And hopefully you see now that this is the squared L2 norm of our error vector epsilon underscore. Because if there was the square root, then this would be just the L2 norm. But since there isn't, it's the square of the L2 norm. And since now we know that norms induce metrics, we have that the squared L2 norm of our error vector is equal to the square of the Euclidean distance between our prediction vector and the true label vector. This will be our empirical risk. And recall that our prediction model is the inner product between any observation x and our parameter vector w. And recall that this inner product is the vectorized implementation of our hypothesis, which we will call f. So this is f of x. F lives in the hypothesis space we search. And also this is the prediction that we make. And following the empirical risk minimization approach means that we now select the parameter vector w for which the empirical risk is minimized. So the solution is called w star, and this is the argmin of our loss. And observe that this optimal parameter vector w star induces our ideal prediction model, the solution to our empirical risk minimization procedure, which we will denote as f star. And this is defined as the inner product between any observation and the ideal parameter vector w star. And this also lives in our hypothesis space of linear models. What I will now show is that the mean squared error, this is the mean squared error, is convex in its argument, the parameter vector w. And knowing this, we can find the minimizer w star by finding the point where the gradient of the mean squared error is the 0 vector. Because for convex functions we have that any local minimum is also a global one. And we have that minima of a function live precisely at those points where the derivative is 0. And since we are in the multivariate case, we want to find the points where the gradient is the 0 vector, because at those points we will have our minimum. And since I will show that the mean squared error is convex, we will know that any minimum we find will also be the global minimum. And this is useful because we will see that we arrive at a closed form solution to our empirical risk minimization problem, which means that we don't have to employ any kind of iterative optimization procedure. We can directly find the solution using some kind of closed form formula. Now at this point I've been talking about convexity so much without actually having defined it properly. And this slide I will do that, and I will also give you some intuition behind convexity. So a function f that maps from Rd to the reals is called convex if and only if for every scalar gamma in the unit interval and every vector pair AB in Rd, we have that the following inequality holds. F of gamma times A plus 1 minus gamma times B should always be smaller or equal than gamma times f of A plus 1 minus gamma times f of B. So we've encountered this before, but what does it mean actually? So first let's observe that the fact that gamma lives in the unit interval implies that 1 minus gamma also lives in the unit interval. And they form a complement, gamma and 1 minus gamma, meaning that gamma plus 1 minus gamma will be 1. So why is this useful? Let's consider 2 points. So point A, which for this example is just 1, 1, and point B, which is 2, 2. Now let's consider these linear combinations of these 2 points, where the scalars in front of the vectors add up to 1. So this first example is 1 times point A plus 0 times point B, which is just point A. In this example, we have 0 times point A plus 1 times point B, which is equal to point B. And now if we split the weight of these vectors evenly, we have 1/2 times point A plus 1/2 times point B, which is the point or the vector 1.5, 1.5. And this lies exactly on the line connecting points A and B. And you will observe that any linear combination of points A and B where the scalars add up to 1, we have that these points form a line. So gamma times A plus 1 minus gamma times B describes a line connecting points or vectors A and B. And this is the line. Now let's have a look at this illustration. We have on the x-axis some just one-dimensional points A and B. And on the y-axis we have function values with the values on the x-axis as input. And we have this function. It will turn out to be convex. We will see that in a moment. And let's just find points A and B and the corresponding function values fa and fb, fa and fb. Now in convexity we have this inequality. This means that the function value of gamma times A plus 1 minus gamma times B should be smaller or equal than gamma times f of A plus 1 minus gamma times f of B. What this means geometrically is that for any point between A and B, this is this red bit here, we have that the corresponding function value, and this is the plot within this red frame, should be smaller or equal than the line connecting fa and fb with the scalars gamma and 1 minus gamma. So here's fa and here's fb, and from this result we observed that gamma times f of a plus 1 minus gamma times f of b is the line connecting the point fa and the point fb. So using the color coding of this illustration, we conclude that convexity means that all blue function values in the red region, so these ones here, are below the orange line connecting function values fa and fb. So a really useful property, which is a direct consequence of convexity, is that convexity implies that every local minimum is also a global minimum. And just as a counterexample, we consider this non-convex function. And we can see that this is indeed not convex, because if we were to take this function value as an example and this one, and we were to connect these two function values with a line, we'd see that the graph of the function exceeds the line in some intervals. And hence this function is not convex. But what we can see is that it has two potential candidates for global minima. And this will not be the case for convex functions. For convex functions, it is always clear that any local minimum will be a global one. But how do we find out whether a function is convex? Because we don't want to draw graphs all the time and connect function values with lines. So there's the second derivative test, and it states that if the second derivative of f, function f, is positive for all input arguments, then that function f is convex. Now, as a really simple example, consider the function x squared. Then the first derivative of that function is just 2x. And since we're interested in the second derivative, we differentiate again, and we find that the second derivative of x squared is just 2. And this is always positive for any x. And indeed, if we were to draw this simple function, this quadratic, we see that this indeed is convex. But in machine learning, we are not usually interested in univariate functions. So we deal with multivariate functions, and there's a similar notion, a second derivative test for multivariate functions. And if you think about it, the second derivative of a multivariate function is the Hesse matrix, where you collect all the second order partial derivatives of a function. And we want this object H, the Hesse matrix, to be what's called positive definite. This is a positivity notion for matrices, essentially. Because in the univariate case, we wanted the second derivative of a function to be positive for all input arguments. And in the multivariate case, we want also some positivity notion for this second derivative object, H. And the positive definiteness of this matrix H, the positivity notion of H, is defined as follows. So for every vector in Rn, which is not the null vector, we want that x transpose times H times x is larger than 0. And observe that this vector matrix vector multiplication yields a scalar. If you were to write out the dimensionalities of these individual objects, you will see that this indeed will produce a scalar. And this positivity notion is indeed similar to the positivity notion in the univariate case, because in the univariate case, you want your second order derivative to be positive for all input arguments x. And in this multivariate case, you want your matrix H to always produce a positive number if you multiply any vector x from the left and the right. So what I'll do now is I'll show that the mean squared error, our loss function, is convex in the parameter vector w. So let's start out by writing out our definition of the mean squared error. And recall that the mean squared error is the sum of squared deviations between our predictions y hat n and the true labels yn. And then we divide by the number of observations we have. Hopefully on a previous slide I was able to convince you that this mean squared error is equal to 1 over n times the squared L2 norm of our error vector epsilon, which is the difference between the prediction vector y hat and the true label vector y. And what we'll now do is that we write out our prediction vector y hat explicitly by using the vectorized implementation of our hypothesis on the entire dataset. Recall that this was x, our data matrix, feature matrix, times the parameter vector w. And there is a standard result in linear algebra which states that the squared L2 norm of a vector v is equal to v transpose times itself. And from this we conclude that the squared L2 norm of xw minus y is equal to xw minus y transpose times xw minus y. So we are able to make this transition. And if we then transpose the terms in the bracket, we arrive at this expression. And if we now multiply out all of these terms, we arrive at this larger expression. And we observe that every term in this expression yields a scalar. So if you write out the dimensionalities of these objects, you will see that the multiplication of these vectors and matrices will yield a scalar for all of these terms. And this makes sense, right? Because the mean squared error should produce a scalar. And so far we've just rewritten our expression. So this should be a scalar. And observe that real numbers or scalars are symmetric, which means that if we take the transpose for any x, which is a real number, we have that x transpose is equal to x. And since all of these are scalars, we have that the transpose of any of these is equal to the expression itself. And this is particularly useful for this bit here, because we can now see that this thing here on the left is equal to that thing, which is on the right. So we have the same term twice, essentially. And also for this bit, we can see that this thing is equal to that thing, where we have the transpose of this product instead of transposing the individual terms. And from earlier, we recall that such an expression yields the squared L2 norm of the vectors contained in the braces. And similarly, we have that this is the squared L2 norm of the true label vector. So let's tidy this up and write all of this out again. And finally, we have rewritten our mean squared error in this fashion. And again, we want to show that the mean squared error is convex in W. So far, we have only rewritten this expression. So what we'll now do is we show that the Hesse matrix of the mean squared error is positive definite, because this will imply that the mean squared error is convex. And since the Hesse matrix is the object containing the second order partial derivatives of the mean squared error, we first have to find the gradient, because we can use the gradient, the collection of first order partial derivatives, to arrive at the Hesse matrix. So let's first find this gradient. So since the gradient is a linear operator, we can push out this 1 over n term and apply the gradient to each of these individual terms. And right away we take notice that the gradient of the squared L2 norm of the true label vector will be the null vector, because there's no w anywhere in this expression. And for this bit, we also can find the gradient quite easily. We just get rid of this w, and we are left with this expression. And for this bit, we arrived to this gradient. And it might not seem really obvious that this is the gradient of that thing with respect to w. But be assured that this is a result from linear algebra. You can look it up in the what's called matrix cookbook if you want. So the gradient of the squared L2 norm of xw is that thing. Someone derived it, put it into the matrix cookbook. You can look it up, or you can derive it yourself if you have the time. And maybe just to give you some intuition of why this is plausible, at least, we have that this thing is equal to that expression. And we observe that this is somewhat like a square of the parameter vector, right? We have W transpose times something times the parameter vector. And if this was the univariate case, this would be then W squared, and the derivative of that would be 2W. And then we multiply 2W with that thing, and lo and behold, this is the expression. So I know it's kind of hand-wavy, but that's how I think about it. And with this, it's now really easy to find the Hesse matrix now. So we find the gradient of that thing with respect to W again, and we see here's no W. So all that's left to do is to find the gradient with respect to that thing. And in that case, it's really simple. We just get rid of that W and we arrive at this Hesse matrix. And then we can take this factor of 2 out, and we arrive at a 2 over n times this what's called unscaled empirical covariance matrix x transpose x. And this object is of dimensionality d plus 1 times d plus 1. And we observe that this is indeed positive definite. This is what we want to show. And we can see this by checking the definition of positive definiteness. So for every vector v in R d plus 1, which is not the null vector, we have that this expression, we have to check whether this is positive for all v, is equal to this bit, right? Because we can transpose these two factors at once instead of individually. And then we arrive at this bit. And recall again that we have that such an expression is the squared L2 norm of these arguments of the braces. And we arrive that this expression is equal to the squared L2 norm of xv. And the squared L2 norm of any vector is positive, unless the vector in it is the null vector. And for this it's never the case that X is actually the null matrix. This would then yield the null vector in this multiplication, because a feature matrix, which is the null matrix, is essentially no observation at all. So as long as you have any observation, this will never be equal to 0, but strictly positive. And with that, we have shown that the mean squared error is convex in W. And now that we've shown that the mean squared error is convex in its argument, the parameter vector, we can be sure that if we find a solution to the minimization problem, that this will indeed also be a global solution. And we will call this global solution to our optimization problem W star. And we will see that this has this closed form solution that we can easily compute. So recall that the gradient of the mean squared error function is this gradient. So we've computed this before, we don't have to do it again. One thing that we will change in this expression, however, is that we will not multiply this parameter vector W from the left using the transpose, but instead from the right. So we arrive at this expression, and this is indeed equal. So it doesn't matter whether you multiply the parameter vector W from the left or the right, it will produce the same object. And then in order to find the solution W star, we only have to do some very basic manipulations. So again, W star is the solution to our minimization problem. It's the argmin of the mean squared error. And for this, we set the gradient of the mean squared error to the null vector, the 0 vector. And this is equivalent to setting this expression to the null vector, again, because this is the gradient of the mean squared error. And we observe that all of these factors don't matter, so we can cancel them and arrive at this equality. And then we can add this X transpose Y to both sides, and we are left with this equality. And finally, we want to find the minimizer W. So we have to get rid of this X transpose X. And we do this by multiplying X transpose X inverse from the left. So we have this inverse on the left, they will cancel, and we will have that X transpose X inverse on the left side of this right-hand expression. And this is the solution to our problem. So the minimizer of our mean squared error function is W star, which is equal to X transpose X inverse times X transpose times the true label vector Y. And this is what we have here. And this proof is also done. All right, so up to now, we've only considered the case where the true relationship between inputs X and outputs Y is truly linear. So what we did was that our model was a polynomial of degree 1. This was also the hypothesis space we were searching. The hypothesis space of linear models, polynomials of degree 1. And recall, any prediction Y hat n was the inner product between an observation xn and our optimal parameter vector W star, which we found on the previous slide. And this is our linear model. This is our prediction. But you will seldomly find a dataset where you only have like true linear relationships between your inputs and outputs. So the question now arises, what do we do if the statistical relationship between inputs X and outputs Y is nonlinear? So what we need to do is we have to increase the capacity of our hypothesis space H, and we can do this still using some linear formulation. The inner product is a linear function, but we can apply what's called a nonlinear feature map to our observations. The feature map phi, let's call it phi, takes as input any observation and produces a vector of larger dimensionality than the original observation. And in it you will find the leading one for the bias term, but also nonlinear representations of your original features. So we have the original feature xn1, the first feature of our observation vector, a feature vector xn. But we also take it to the square. We might take the sine or cosine of that feature, any kind of nonlinearity you want to apply. We can also multiply features from the original feature vector, in this case the first and the second feature. We can find the product of any two features and take one of those to the square, and one we leave unchanged. Anything you want to do, really. And if we go for these polynomial features, then we call our problem not multivariate linear regression, but instead polynomial regression because we have polynomial features and we can essentially produce a polynomial linear regression. And just as a side note, because I just realized that I failed to define this on the next slide, let's do it here. So the feature mapped dataset X is just a dataset where we collect the feature mapped observations instead of the usual ones. And this object is of dimensionality n because we still have n observations, but we have more columns this time. And the number of columns is the length of any feature mapped vector. What's so great about this approach is that we now have access to non-linear combinations of our features as well as non-linear representations of those individual features. So what we can do is we can fit non-linear models to the data while still retaining our linear formulation, because we still have this model formulation of any prediction being the inner product between a feature mapped observation and the parameter vector. It's still a linear combination, and our solution doesn't change actually. But instead of the plane axis, we have now the feature mapped axis in our solution formulation. But I hope that you can recognize this solution. Nothing has changed really. Of course, there's a caveat to that. So let's just assume that we have a feature mapped observation and it is of dimensionality k. And let n be the number of observations that we have available in our dataset. Then the total time complexity of evaluating this expression, so finding the optimal parameter vector, this scales quadratically in the number of features we have. So the biggest pain point, a computational pain point, is finding the inverse of this expression, because it is of dimensionality k times k. And this is why you have this k squared term here. And if k is really large, this might become infeasible, actually. If you're interested in seeing how you arrive at this time complexity, because there's still something you can do about making this more efficient using some matrix decompositions, then have a look at this Stack Exchange thread. But the main takeaway is that the dimensionality of this expression, this k by k dimensional object, increases rapidly with the degree of polynomial we want to fit, or the number of interaction terms we want to implicitly want to fit to our data. So later we will talk a little more about model selection. And what it means is even though we have this solution to our convex optimization problem, we still have to deal with what's called hyperparameters. And a hyperparameter is any kind of parameter that is not explicitly optimized when running your learning algorithms. So one hyperparameter, for example, would be the feature map phi. So there are many choices of feature maps. Which one is the best for your problem? You don't know. So you run multiple of these evaluations and see which W star leaves you with the best fit to your data. And running this numerous times for different feature maps might just be intractable for your problem. But of course, there are solutions to this problem. So the first one is what's called the kernel trick. And this will be the content of next lecture. And there are also gradient-based optimization procedures, which I'll cover in a later module of this program. But essentially, the main idea behind gradient-based optimization is that you find an approximate solution to your problem instead of a analytical one, which might take more computation to find. But often what you have is that the approximate solution, which you find by running gradient-based optimization procedures, is good enough to solve your problem. So another problem that you have with polynomial regression is that you have to be careful about the power of the hypothesis class that you implicitly define by choosing a polynomial of degree m and interaction effects that you want to fit to your data. In the last lecture, we talked about over and underfitting. So let's review these concepts now in the context of polynomial regression. Now we have the red model, which is a polynomial of degree 1. So just a linear model without any polynomial feature maps. And this underfits our data. So the true relationship in the data, we can see this because we only have one input feature, is a quadratic one with some noise. And we see that a plain linear model doesn't fit it. Then we have the polynomial of degree 300, and this heavily overfits the data. You see these large oscillations. And if we were now to introduce new data points, new unobserved data points, this overfit model will likely produce a very high error on these new data points. And then we have the blue model, which is just a quadratic, so a polynomial of degree 2. And we see that for this data set, the fit is just right. So when selecting your feature maps, you have to be careful not to introduce too much flexibility, because given your finite data set, you might run into the danger of introducing too much flexibility in your hypothesis class, leading to models that don't generalize well. But there's one approach in model selection that seems to work really nicely in practice, and that is introducing a very powerful hypothesis class so that you have a lot of really good functions to choose from, and you discourage the selection of an implausible model by means of regularization. So what does it look like? So we have our loss function again, our error function, and we will use the squared error, squared deviation again. But this time we will drop the 1 over n term because it doesn't matter in optimization, right? Because the solution to a scaled problem is the same as the solution to an unscaled problem. But what we'll now do is we'll introduce what's called a regularization term. And this is a factor lambda times the magnitude of our parameter vector. So it's the sum of all squared parameters we have in our parameter vectors. So we start counting with the bias, which is indexed with a0. And we need k parameters. So we have the summation starting from k equals 0 to k minus 1. And writing it out in our matrix vector notation, we have this expression of our loss. So we include the scaled square of the L2 norm of our parameter vector in our loss function. And what it does effectively is that we penalize highly implausible models, because these highly overfitting models that we've seen on the previous slide, where the degree of the polynomial is so high, you have these large oscillations in these polynomial models of high order, because you assign large parameters, in magnitude large parameters, to the polynomial terms in your linear regression. So what we do by penalizing the magnitude of the parameter vector is that we find solutions that are more reasonable, more moderate, because the parameters in our linear regression will then be of moderate size. So lambda is essentially the importance that you give this magnitude in your loss calculation. So the larger lambda is, the more weight you give the importance of the squared L2 norm of the parameter vector. And this is a hyperparameter. You don't optimize it explicitly by running our optimization procedures. You tweak this more or less by hand. We will introduce more elaborate hyperparameter search schemes in a future module. But for now, consider this just a hyperparameter that you tweak yourself. And minimizing this new cost function has a solution that looks very similar to what we found before. So W star almost looks like what we had before, but this time we add lambda times the identity matrix to the object that we take the inverse of. Note that there's an alternative formulation of ridge regression. Oh, by the way, this entire idea is called ridge regression. And in this alternative formulation, we don't penalize the bias, so WO. And this makes sense. We don't want to penalize our expectation of the true label in absence of any observation, X. Right? So this was our bias term. And if we don't penalize WO, the regularization term, this thing here, becomes this one. So we start the sum not at k equals 0, but k equals 1. And the solution is really similar to this one, but instead of lambda times the identity here, we have lambda times a, where a is almost like the identity, but on the first diagonal entry, you don't have a 1, but instead a 0. And now let's see what the hyperparameter lambda does to our ridge regression. So we have two illustrations. Let's first look at the left one. So for both illustrations, we have linear data, and we fit 3 different linear models to that data. And the difference between the models is the regularization term associated with each model. So the first model, the blue one, has no regularization. The green one has a lambda of 10, and the red one has a lambda of 100. So the unregularized model, the blue one, is just a linear regression fit to our noisy linear data. So this is what we discussed at the beginning of the lecture. And we see that as we increase lambda, we have that the slope of our linear model vanishes. With a very large lambda, we are essentially left with a flat model that just gives for any x any observation the same prediction, and this flat prediction, this red one, will be the average of the label. And now for the more interesting case where we have nonlinear feature maps in our model, we have that this unregularized model has this small oscillation pattern. And given that this is linear data, we know this because we generated it ourselves. This model is already overfitting the data because there's no oscillation pattern in this linear data. And what increasing the value of lambda now does is that it straightens out our model. So it gets rid of this oscillation and it becomes more tame and linear-like as we increase lambda. So the red model is also not a perfect straight line, but it is much more of a straight line than the unregularized model. And finally, for this last slide of this lecture, I want to prove that the solution to ridge regression, so including this regularization term, is indeed what I proposed on a previous slide, where we include the scaled identity matrix in our inverse term. Now we start by writing out our loss function again. So we have this squared L2 norm of our prediction vector minus the true label vector. And this time we add the scaled magnitude of the parameter vector. And from the previous proofs, we know that the squared L2 norm of any vector is just the vector transpose times itself. So let's write it out for both of these squared L2 norms. And now we find the gradient of our loss function again. And for this term, we have already found the gradient before. So I'll just copy it from what we had earlier. But this term is new, so let's find the gradient of it. So it's lambda times the gradient of W transpose W. And this is what I mentioned before. This looks like a quadratic in the multivariate case. And the derivative of a quadratic is 2 times the term that you take the square of. And in this case, it's similar. So it's just 2 lambda W. This is the gradient of this expression. And again, we set the gradient vector to the 0 vector. So let's set this expression to the 0 vector. And similarly to before, we can get rid of these factors because they don't matter in the optimization. And we can also get this expression from the left to the right side by adding it to both sides. And this is what we have here on this line. And now we observe that for the left-hand side, we multiply W from the right to both expressions. So we can rewrite it as such. This is equivalent. And what we finally do is, in order to arrive at the W, we take the inverse of that entire thing, multiply it from the left to both sides, and we arrive at this solution. So W is equal to the inverse of this thing times X transpose true label vector. And this is what we have here. So this concludes the final proof of this lecture, and I'll be delighted to see you again next time where we talk about the kernel trick.